we saw two kind of frameworks last week, and again I would like to clarify why are these frameworks there. And so remember, in the abstract algebra course, we had this set of numbers, right? Integers, real numbers, all of those satisfied some properties, right? And we can say that all these set of numbers, please mute your mic if you are not asking a question or discussing something. Thank you. Yeah. So in the abstract algebra course, you saw that numbers like integers, real numbers, complex numbers, all of those could be thought of as, we abstracted out to them to make a abstract object. And we said that all of these kind of come from this particular kind of construction. What were these objects called? Do you remember?
Fields.
Sorry?
Groups, rings, and fields.
Groups, rings, and fields, right? And it's in a sense, it's a similar idea. We want to give a framework where every kind of random experiment can be put in. We started with discrete sets, and when we did that, we kind of found this old framework to be very, very helpful, and it mirrors what we saw in our high school. The idea was all the distinct outcomes were in a sample space, and then any event was any subset of the sample space. So every subset of the sample space was a possible event. And then the probability distribution function was from the sample space. Remember, it's a sample space to 0, 1. This was the simple thing, but then we saw that, it was not able to capture all the random experiments we wanted. Specifically, when we had continuous cases, we had infinite samples. Okay, so some of the infinite examples can be taken care of by the old framework, but clearly when we talked about picking a random number between 0 and 1, our old framework was not able to take care of that situation. And then we described a new framework. The framework captures all these random experiments, and then, whatever properties we develop from this new framework, these properties will be applicable to any random experiment which can be put up in this new framework. And in this new framework, this was slightly general framework where, we had the same sample space, set of all distinct outcomes, but events changed. We had to explicitly say that these are the events where we are interested. And then the probability distribution function was from f to 0, 1 instead of from omega to 0, 1. And this f and this probability distribution function needed to specify certain properties. Again, most of the time you will be using the old framework. This is something which should be crystal clear to you, but you should remember that in some cases, we have to go to the new framework. That's why I have specified. Slowly, when you work with it, things will become more clearer, but you should at least know that when we talk about real cases, the old framework is not sufficient. And this new framework, we have to remember, what is a sigma algebra? It's a set of interesting events. That means it has to be a subset of the power set, though any subset of power set is not good. It has to satisfy certain properties, specifically these three. The complete set should be in F. If A is element of F, then A complement has to be element of F. Any countable union should be in F. That will imply any countable intersection is also in F. Okay. So these are the important properties of sigma algebra. So in the new framework, you start with a sample space, you define F, you define the set of interesting events. They should satisfy the three properties mentioned above. And then the probability distribution function is going to be a function from the set of interesting events to a real number between 0 and 1, which satisfies these properties. Again, these properties might seem like a long list, but you should realize that, they are very intuitive. None of them are in some sense very a weird property or something. This is what you would expect them. And just these properties are good enough to prove most of the things which you saw in the old framework. For example, we saw that just by using these things, we could prove that P of A union B, when they need not be disjoint, is equal to PA plus PB minus PA intersection B. In old framework, it was easy to prove. In new framework also, it's not difficult, but it requires a slightly different proof, which we saw last time. And again, the things to remember, most of the time, old framework will work. Most of the properties which you saw in the old framework will work even for the new framework. So don't worry. And how to prove them? By experience, you will learn that. And at least in this course, most of the time when I talk about sigma algebra, the Borel sigma algebra will be good enough. This is the sigma Borel sigma algebra is one particular case. Like when you talk about groups, integers is one particular case, real numbers is one particular case. Similarly, when we talk about sigma algebra, one of the simple case is Borel sigma algebra when we talk about all possible open intervals, their unions, intersections, and so on and so forth. And that is the one we will be using almost all the time. Let me take an example to show how you can kind of think of how you can think of this new framework slightly in some cases. So suppose a family has 5 kids. The question is, what is the probability that it has more girls than boys? What would be the sample space? In this case?
Boy and girl.
Sorry?
Like one boy, one girl. That should be the sample space. Because
why? Is that the possibility of all distinct outcomes?
So the combination of genders.
A string of 5. String of 5.
Exactly. It is string of 5 characters. Let's say G is for girl and B is for boy. So all these strings of this kind would be the sample space, right? So how many elements are there in my sample space?
32.
32. Very good, right? And then I can say this is, again, I want to describe everything in the new framework. I should describe F. And since everything is discrete, I can kind of say that this is my sigma algebra. I don't even have to prove that this is a sigma algebra. It satisfies all the properties. And if this is the case, what event are we looking for? Can you
The number of G's in the string is greater than the number of B's.
Right. Strings where number of G's are bigger than number of B's. Okay, call this event A. Right. And any guesses what will be the probability of A?
Half.
Okay. Why did you say half?
Same for boys and girls. Same for, like, if we make an event that is the number of B's greater than number of G's, and then their number cannot be equal because there are 5 kids, right? So these two events are exhaustive and
they have equal probability because of symmetry, right?
Yes, sir.
Great. So let me try to capture this intuition by defining a new F and a new samples, by defining a new F. So my sample space will remain the same. Notice what is my F? Remember what was A? A was the number of strings where G's are bigger than number of P's. Okay, first question, is this sigma algebra? How do you verify that this is a sigma algebra? There were three conditions, right? Yeah.
So suppose
Mhm.
because like the omega belong to F,
Very good.
and
If
if A belong to F, then A complement is also in F,
very good.
and
And
then
the
unions, countable unions is also in F.
right. So now this might take a few minutes for you to check, but you can easily check if that AB is element of F, then A union B, and even more countable unions. There is no need for countable union. Just this will also be right. So this is a valid sigma algebra, right? And now if I want to think about it, as the intuition suggested, probability of A should be equal to probability of A complement. And what do I know? I know that probability of A union B should be equal to PA plus PB if A and B are disjoint. If I take B to be A complement, this means 1 is equal to PA plus PA complement, implying PA is equal to half. This might seem boring to you. What I'm just trying to emphasize is that you can even put your previous experiment in the new framework. And it kind of captures. This is probably the very simple example where your sigma algebra is not the complete. F is not the complete. Sorry.
The power set of the
The
event
power set.
sample space.
Exactly. Exactly. Before that, whatever examples you have seen, your set of interesting events, your sigma algebra was always the power set. And this is one example where you can define everything. So the previous question, even if you model it like this new way, this is fine. Notice I won't even talk about here the probability that I have, three girls and 2 boys in the family. None of those are talked about. But this is enough. This new framework, new kind of sigma algebra is good enough to capture my question. Though it is not very detailed. If you want to ask, okay, what is the probability that I have 4 girls and 1 boy, or 4 boys and 1 girl, I should probably go back to the nicer and more general sigma algebra. The idea is to show you that different sigma algebras are possible. And obviously the place where we will actually need it is when we talk about continuous case. Right? Whenever we have continuous sample spaces, you saw that it was not possible for us to define the probability of we were not able to assign the probability to a single point. That was creating a problem. And then we said that we will have a different sigma algebra. What was the sigma algebra? What was it called?
Borel sigma.
Borel sigma algebra. And what was it intuitively? It contained
Open intervals.
right, all open intervals, their intersection, union, so on and so forth, right? Because remember, just if you take just all open intervals, they will not form a sigma algebra. So we should take their union, their intersection, etc. Complement, all those have to be allowed. So this is the smallest sigma algebra which contains all open intervals. And the probability distribution which we will think on that would be the uniform probability distribution. That means the probability of an interval or an element of Borel sigma algebra is going to be proportional to the length of the interval.
Sir,
Yes.
in Borel sigma algebra, it contains all the open intervals. Is it necessary that it should it is exhaustive to that, or it can contain closed intervals too.
So this is something which you can take it as an exercise. Now you know that all open intervals are there, their unions and intersections are there. Can you create a closed interval using these operations?
Yes.
Okay. And now, so that's an see again. It's not going to matter because the probability of picking something in 0.5 is going to be same as 0.5. So this technical detail about what exact elements are there in Borel sigma algebra, that's more of a mathematical question which people bother about, but you can definitely figure that out. That's not hard. But you see here, right, that the probability of these two things are going to be equal.
Yes, sir, it would be same, but
Would be
I
same.
just said that out because
Yes. So
if you want to write, you
yes,
have to make proper argument.
it's a good doubt. Think about it. If you can't come up with an answer, ask, and we will sort it out.
So individual elements can be included in a particular set when we think of this Borel sigma algebra, right? Like
Sorry,
one
I
set
did
will,
not hear you clearly. Can you repeat your question?
individual elements can be considered too, right?
Again.
Like one set contains 0, another set contains the open interval 0 to 1. One set contains 1, and then we take the union, and then we can call it closed.
Right. So again, I would be very happy if one of you writes this proof in Hello. Okay. So these two questions in Borel sigma algebra, do you have closed intervals? Do you have singletons? If you are, again, we won't be needing them in our applications and things like that, but it's a very nice mathematical question. So take it as an exercise, and if you can write it as a proof, you can figure out the proof of taking intersection and unions. How can you create closed intervals or singletons? I would be very happy to see that. Okay, it's a simple exercise. It's not difficult. What we would be interested in, is this probabilities, and let's say, what do you think? Will this be part of Borel sigma algebra? R1, R2 union R3, R4, where R1 is less than R2 is less than R3 less than R4. Will this be part of sigma
Yes.
algebra?
Yes,
Right. Very good. It will definitely be part of sigma algebra. What will be the probability of this?
probability of the R1, R2 plus probability of R3, R4.
What will the probability of R1, R2?
R2
R2
minus
minus R1
R1.
plus
Plus
R4 minus
plus R4
R3.
minus R3.
Right. And if you just double the interval, you just normalize, you divide by 2 and things like that, right? That's how practically you would be using the continuous sample space almost all the time. Is there any question? Okay, then let's go to Bertrand's postulate, and this was the question. Let me give you a minute to read this question.
Excuse me, sir.
Yes.
So in the previous slide, you asked us to write the proof of that. Sir, I guess that's not true. So like.
So you prove that it is not true. Right?
Okay.
So we have to figure out mathematically, are singleton sets allowed in Borel sigma algebra, are closed sets allowed in Borel sigma algebra?
Okay.
Right. And whatever is the answer, you let me know.
Yeah.
So Aditya, I don't understand your question. Does proportionality includes higher powers of length? What do you mean by higher powers of length? Again, it's very hard for me to look at chat. Can you unmute and?
Like it could be proportional to the square of length or cube of length.
Yeah, sure. You can see again, the framework is very, very general and you can define it. You have to normalize it in a different way. And you can say that, the probability will be proportional to the square of the length and things like that. The point is, are you able to satisfy the properties written in the axioms? Can you make your probability distribution, P of omega should be 1. If you take the probability of two disjoint things, is it going to be, and this is where you should be careful when you talk about square and cube. Can you say that probability of A union B is going to be PA plus PB? Think about this, and then you will see what is the answer to your question. The point is, again, I'm just giving you one example which will be very, very useful. I am not saying these are the only examples possible. I am not saying Borel sigma algebra is the only sigma algebra. There are many, many sigma algebras. We will mostly deal with Borel sigma algebra. When talking about Borel sigma algebra, we will talk about uniform probability distribution. I am in no way saying this is the only probability distribution possible mathematically. There are many. We will mostly be concerned with the uniform probability distribution where it is going to be proportional to the length. Can it be proportional to the length square? You have to be careful. You define everything and then check whether the axioms of the probability are satisfied or not. Remember, it said P of omega should be 1. P of A union B should be PA plus PB whenever A and B are disjoint. Okay, and I think that is where you will see the problem specifically for the poles. So yes, definitely other uniform probability distributions are possible, and we have to check a particular one to see whether it satisfies the properties we had listed. Okay, now this question, I think you all of you have stared at it a bit, and if you remember, all of you got the different answer. Any answers at this point of time? Just unmute yourself and say what is the answer.
1/3.
Okay, 1/3.
Half.
Okay, good.
2/3.
1/4.
Okay, 1/4. Okay, so at least these we will do. But now, can someone guess what is the problem here? Why are we getting all these answers?
So the number of chords are infinite.
The number of chords are infinite, yes, but you are close. But then, exactly what is the problem? Which is why we are getting all these different answers.
Maybe we had to do it.
For different
So there's no
cases, we are
proper way of
taking-
describing the chords. We're using different ways to describe the chord.
Right. So in our language or framework, what is different in each of these cases?
The sample
The sigma
space.
algebra.
Data is not complete.
Yes, the sample space, and that is why the sigma algebra is different. Since you might be wondering what happened, why are there three, what are the three answers I am talking about? So let me just tell you this, right? So first example, in the first sample space, I will choose a random endpoint on the circle in the sense that, I can fix one endpoint. I can say that my chord, my D aligns with, see again, the rotation, how should I say it? The orientation of the triangle is not fixed. I'm worried about the chord. Let's fix the one endpoint of the chord, and then I will draw the triangle from there. The length of the side does not change, right? And now, if one endpoint of the chord is fixed, where should E be so that the length of the chord is larger than the side of the triangle? Where should E lie?
BC.
Right? It should lie between B and C. And it is now clear that, so choose a random endpoint on the circle, then DE is larger, implies E is between B and C. And this will give you the answer.
1/3.
Right? So look at this circle. What is the probability? If I take a random point on the perimeter of the circle, what is the probability it lies between B and C? Obviously 1/3. Okay. Now, another way to pick a chord. This is a different sample space. So let me start. Let me look at this radius, and I will say that my center of my chord is going to lie on this radius. Okay. So my chord could be here, here, and here. And then by doing some simple geometry, you can see that where should my midpoint lie?
Between the midpoint and center of the
Right, very good. So if I call the midpoint F, then my midpoint of the chord should lie between O and F. Between O and F. Right, and what is the length of OF? By geometry or trigonometry, a bit of trigonometry.
R/2.
R/2, right? So that means, what answer do you get?
Half.
Half. Very good. Right, and then you can say that why am I fixing why am I fixing one radius?
So shouldn't the answer be 1/4 probability?
Right, exactly. So I'm going to show you 1/4 also. You might say that whenever the
No, for
center,
this question, like for if you choose a chord of midpoint,
see again, what is the sample space? If I fix my radius and say that
okay.
my sample space is my midpoint lies anywhere on this particular chord, then answer is half. But if you say that anytime my midpoint, so choose a random point on a, I should say, on a particular radius.
Okay,
Right?
sir.
And if I choose a random midpoint of the chord, then it should lie in a circle of radius. Where should the midpoint be in a circle of radius?
R/2.
What is random
R/2.
midpoint?
Sorry?
I mean, what is random midpoint, sir? I mean,
okay.
midpoint can only be midpoint.
Yeah, sorry. That is the, so I should say choose a midpoint of the chord randomly. That is the correct. Thank you very much. Yeah, that was my mistake. Right? That's how I should put it. Is that clear now?
Yes, sir.
So it is not clear.
Sorry?
It should lie in how was the solution 1/4?
So this is because exactly the same argument, but now see, whenever the midpoint lies at a distance of less than R/2 from the center, then the chord will be bigger, right? That's what we saw, even from the previous side.
Yes.
So it's just the sample space is different. In the second part, we were saying that I fixed the radius and midpoint lies anywhere on this radius. In the third case, we are saying that my midpoint can lie anywhere, right? So it
Yes,
has to
I
lie
got
in the
it.
R/2 circle.
Yes, sir.
So in some sense, and this is the opinion we will go by, we will say that none of the answers are incorrect. The question was not well specified. When you describe what is the random chord, then I will be able to answer the question. You have not told me what is the correct way to specify the random chord. Now, if you read about the Wikipedia entry, if you look at the Bertrand's postulates, people talk about what should be the correct way of picking a random chord. But if you remember, I told you this in this course. Please unmute yourself if you are not asking the question. If you are picking the random chord, if you're doing a physical experiment, how you do that physical experiment is not really a concern for me. You should specify finally to me what is the sample space. Then I will give you answers on the probability of things like that, right? Again, there are ways in which, because of symmetry, and say people will say, oh, 2 is a better way to think about as compared to 1. 2 is a better way to think about than 3 or something, but we will not worry about this. For us, if you give me the particular sample space, then I will give the correct answer. One small point which I want to clarify here is, can you hear me?
Yes, sir.
Yes, right. So yeah, one small point which I want to clarify, which might be a confusion in some of your minds, is this 2 and 3, right? there is a one-to-one, in some sense, correspondence between the sample spaces. Is that good enough? So what is the correct answer? None or all. That depends on how you want to look at it. The question was not well posed. But in this case, the confusion is, oh, if I look at all these sample spaces, it seems there is a one-to-one relationship between the sample spaces. Shouldn't the answer be same if I have one-to-one sample space, one-to-one relationship between the sample spaces? That is not correct. That's not the correct intuition when we talk about infinite sample spaces. This can lead to wrong notions. So let me just clarify this. So isn't one-to-one mapping between samples enough? The correct answer is no, it is not enough. You need to describe sample space clearly to me. Let me give you an example where this might be a problem. What is the probability that my x square is between 4 and 9, given that x is between 0 and 6? What do you think is the answer?
It's still not defined.
Sorry? Sorry, I couldn't hear you clearly.
Can't be determined.
Can't be determined because, so what are the possible sample spaces in this case?
Like we can take x square from 4 to 9 as one possibility, and x square from 0 to 36 as one possibility, and x from 0 to 6 as another.
Very good. Thank you. Right. So one of the possibility is omega 1, which is pick x square between 0 and 36. Omega 2. So these are two possible sample spaces. Pick x between 0 and 6.
2 and 3.
No. Yeah, the event would be to 2 and 3. Sample space would be between 0 and 6, right? So that is clear, right? So what is the probability of the correct event in this case?
5/36.
Right. Again, I have assumed uniform distribution, right? When not mentioned, I will assume uniformly. I'm picking uniformly between 0 and 36. What about this? What will be the probability now?
1/6.
1/6.
1/6. And the answer comes out to be different. But obviously, when you pick an x, you're in some sense picking an x square. So there is a one-to-one relationship between omega 1 and omega 2. This is the thing which you should be careful about. Okay, now is the time for quiz. Yes.
Sir, like we can define more sample space, no? Like
Yeah.
x cube is between this.
Yeah. Sure. Yes. But anyway, the time is there for quiz. I will answer more questions once the quiz is finished. Go to the quiz. Remember, there can be multiple correct answers. There is no negative marking. Read the instructions carefully on Hello and start your quiz. It is going to start in 1 minute. I am here in case you have any questions.